Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. So it is my pleasure to introduce Matt Welsh, who is currently Associate Professor in Computer Science at Harvard. I think many of us know Matt quite well. Matt actually usually visits us once.
Third or fourth time here.
Yeah, once a year at least.
Usually, yeah.
And so Matt is going to talk about CitySense, an open citywide wireless sensor network.
Thanks. So this is a lot of the projects that I do at Harvard involve sensor networks in one form or another. I consider myself more of a distributed systems person who happens to use sensor networks as a very interesting class of distributed system. But in looking at sensor networks, a lot of the constraints that you look at in sensor networks, they've got to be small devices, low power, running on AA batteries, that kind of thing. We started looking at this project as an opportunity to change a lot of those variables and ask questions about what kind of sensor network could you build in a different kind of situation. So this is, we have 4 or so PhD students working on this, including Rohan Murthy, who's going to be here this summer working with Ron Veer and G2 and those guys. We have a bunch of great undergraduates working on this project, and this is also in partnership with BBN Technologies, which is a small company in Cambridge. They do a bunch of interesting things, and BBN's working with us on the hardware design and some of the software for this project. So CitySense, basically the idea behind CitySense is we want to have an open sensor network testbed that anybody in the world can program over the web, basically. That consists of, we're budgeted for about 100 nodes, although that number could grow or shrink depending on the funding situation, to mount it on streetlights and rooftops that are basically single board computers with dual 802.11 radios, powered from the streetlight, which is great, so we don't have to worry about batteries and things like that, and various types of sensors attached to them. So we have USB and RS-232, so you could imagine attaching weather sensors, noise pollution sensors, road traffic kinds of sensors, various types of air quality monitoring, and we're trying to keep that open-ended in terms of what exact sensors you mate with this system. And as I said, the focus is making sure that this is programmable. So I'm going to get into some of the implications of that in a minute. By the way, I'm interrupt-driven, and so it's more fun to have a conversation. So if you want to interrupt me at any time, please go ahead. So this is a prototype of one of our nodes. We have, I'll show you in a minute, about 10 of these deployed right now in Cambridge. And as you can see, it's like a Mac Mini size package. Yes? Great question. The answer is I don't know yet. So we started with 802.11. I'm going to come to this in a minute because when we wrote the proposal, we assumed that 802.11 mesh was a solved problem. Some of you in this room will probably laugh at that, but we made an assumption in that was going to be the most cost-effective approach. Okay, so why do we want to do this? Well, the first thing yeah.
I guess from my naive perspective, you've got a bunch of sensors. They don't have any outputs or anything. So there's a bunch of data, or maybe they do, but a bunch of inputs, a network. Why not just send all of the data to a central
Let
place?
me get there.
Okay.
Let me get there, please. Okay. So the first thing we wanted to do is get sensor networks kind of out of the lab and into the field, into the wild. And we've done stuff like on volcanoes. I gave a talk on that here like a year ago. So we have a good feel for how to get sensor networks out into the real world, but this one looked like maybe an opportunity for like a permanent deployment, something that was tied in with permanent power supply from the streetlights, and embedded in a city. And once you do that, I think it changes your relationship between the sensor network and the people in the city, and certainly the government of the city ends up having a lot of interesting interactions with them. So the primary focus of this project is an open programmable test bed. So the way of thinking about this is Planet Lab meets RoofNet. Yeah? So the point is, I don't actually know all the things that people are going to want to do with this. I sure hope I don't know them all. And by opening it up and letting other people push applications into this, they're going to be able to do different things with this test bed. Now, to answer your question, the number one thing that's going to address 90% of the users is to take the sensor data, ship it back over some wireless link back to a central server, and log it to a database. We're going to do that. We are doing that. But for the people that want to do things that involve in-network processing, understanding distributed algorithms, understanding better mesh routing protocols, these kinds of things, they're going to want to actually program the nodes to do different things as a way of prototyping future systems. Okay, so if it was just about collecting the sensor data from the light poles, we'd be done by now. Yeah?
So Matt,
Yes.
So this SensorMap testbed is actually at the high level of power regime than the mode class devices.
That's right. Way higher power. Yes.
And do you see actually what are the sorts of research problems?
Let me get there. This is what the whole talk is
that are
about.
shared and they're all different from the mode.
What this whole talk is about. Thanks. I'm on slide 3. Let me get there. All right. Now, this is my cartoon, not reality. And when I showed this to the people from the city of Cambridge, they kind of freaked out a little bit. But the idea is that each of these dots is supposed to be a node. And we're going to have a couple of wired nodes that are connected to the internet, and they act as gateways for being able to both control and monitor the network and get the data out. This is not intended to imply any kind of causality on the part of MIT. I just happened to put the contaminant source in that part of Cambridge. And so you could imagine an air quality or a bioterrorism monitoring system that is trying to infer the values of a plume that's emanating from a certain point and localize the source of the plume based on the concentration levels and the wind patterns observed by the nodes. So just to give a cartoonish intuition as to the kind of application that someone might want to deploy on this. Okay? I don't think we we put a little mushroom cloud instead. Yes.
How easy it is for people to vandalize pranks, just damage? Are these in plain view? How easy is it to get to these?
They're up high on the streetlights, so hopefully not too easy. We're not so worried about vandalism, to be honest. Yeah. Okay. So. Let me talk about the node. So I'm doing this as a very bottom-up kind of thing, and I'm going to come to the higher-level research questions in a minute. So where are we starting? We said, okay, look, we want to build on basic stuff that's out there already. We don't want to invent this stuff from scratch. So we went out and looked at what other people were doing. We settled on a hardware design that's based on a Socra single-board computer. This is very commonly used. Actually, we just found out that these are no longer going to be available after like 6 months from now, so we have to decide whether to buy up all of our stock now and use them later. They only have 256 megs of RAM. We're not able to use a hard drive because the hard drives are just not going to survive in kind of harsh weather conditions, and so we're using flash memory. And for budget reasons, right now we're sticking with a little thumb drive, 2 gigabytes. We could expand that as time goes on. The enclosure is designed for NEMA 6X, which basically says you can hit it with a fire hose and no water will get in, which is nice. That's probably over-spec'd. And it turns out right now we're running FreeBSD, and you might say, well, why not some other operating system? And the place that we started was Linux, and the reason we started with Linux is that everybody else in this community is starting with Linux because there's all this driver support. Well, it turns out the Linux wireless drivers are completely broken, and they just don't work. And so we have one of the guys on the group is like a FreeBSD guru, and he installed FreeBSD, and it is incredibly stable compared to Linux. So that was kind of a big surprise for me. In order to use this network, we're going to have dual 802.11 radios. I'm going to get into more of the details on the radios in a minute. But the way of thinking about it is one radio will be our radio that we use to control the network. That's our backhaul for basically administration. And the other radio is an experimental radio that the person writing the code will be able to do whatever they want with that radio. So if G2 comes along and says, oh, I've got another version of my mesh routing protocol, he can take over that radio and do whatever he wants with it. Yeah? And so the thing is mounted here, and it turns out the photocell on top of the streetlight, if you unscrew that, there's a 3-prong 120 volt you can plug into, which is awesome. That's not true of all streetlights. It just so happens in Cambridge that we got lucky.
What is the photocell used for?
It turns the streetlight on and off at nighttime. And it turns out that these streetlights are always powered, and they turn themselves on and off. A lot of streetlights in different cities are bank switched, which means that there's a central controller that turns them all on and off, in which case we would not get power during the day. So again, we're lucky that City of Cambridge has this particular, and also we're lucky the City of Cambridge owns their own streetlights, which is not the case in a lot of cities. It turns out in a lot of cities the streetlights are owned by the electric company. So there's a lot of happy coincidences at work here. All right, so the early design of the node was not so pretty. This is the motherboard. We have some antenna connectors. There's like a power strip and a couple of power supplies. I mean, this is really ugly. Not going to be able to mount this on a street light. The sensor is here. We have some radio antennas sticking out, one at the bottom, one at the top, and it's on a tripod and a wooden board mounted, weighed down with the sandbag. So this was just an early prototype. The current prototype is a lot nicer, and it's basically packaged into this small case. The antennas are here. The weather sensor, I'll talk about that in a minute, is here, and it gets its power from the street light. Okay? Just to give you a sense of where we're at with this.
What kind of approval do you need in order to mount on a public utility pole?
Say that again?
What kind of approval process do you need?
That has been a tremendous minefield. We are working very closely with the city electrician from the city of Cambridge, and he is basically donating his time and money and personnel to work with us to get these things mounted on the streetlights. But it's a tenuous relationship because it's not really something that's approved from like a very high level. So it's a grassroots effort right now. Once we want to roll this thing out to the full-scale test bed, we're going to have to go to the city government to make a case that we're going to, you know, these things aren't going to fall off the poles and hit somebody on the head and kill them.
The other ones that probably there are union code and stuff that only electricians.
Yes, there's all kinds of legal things that, yeah, the guy, yeah, that's not a graduate student. Okay, that's a city electrician. Yeah. All right. So, application domains. As I said, we want to keep this open-ended. We don't really know what people are going to want to use this for. We have some things in mind and some things that we put into the grant proposal to the NSF. So the NSF bought those ideas. So they included things like, we're working with people at this Harvard School of Public Health. They have about a zillion things they want to do. They would love to get real-time data on road traffic, weather, air quality, where people are. Yeah?
One other thing, do you have any sort of guaranteed shut-off time? So even though you have this one dedicated radio that's supposed to provide a reliable backup, I mean, you're going to run some software on that, right? And
yes,
that's going to fail. So there might be times when your nodes are.
I'm going to come to this in a minute. I have a whole slide on this.
So like at midnight they reboot.
Yeah, I have a whole slide on that. Yeah, let me get there. But good question. The other one is, there's been a lot of interest in this participatory, opportunistic sensing with people carrying sensors on their cell phones. And what I think is a potentially interesting project is something where you imagine the CitySense nodes are very expensive, fixed, calibrated sensors, and you integrate the data that they're collecting from data that's opportunistically collected by people carrying phones and things like that. All right? Deborah Estrin and other people are working on that kind of thing. We definitely want this to be useful to people who don't care about sensors that want to do wireless networking kinds of things. And so if somebody wants to understand a new link or mesh routing protocol or something, they should be able to run experiments on our test bed, and that should hopefully give them some expectation of how things might work in the real world. And then, a whole bunch of other CS-type applications. So you might imagine somebody building a system that does some form of location-enhanced social networking where it knows where people are, and you use a Twitter-like thing and post what you're doing, and it sends it to the nearest CitySense node, and it shares that information with anybody else in the environment. And you could imagine a bunch of different things that you would do if I had programmable wireless devices in the environment that I could talk to. Yeah? That doesn't have anything to do with the sensors necessarily. Yes? And so, as I said, we want this to be really open-ended. So our focus right now is on building up that infrastructure so that people can do these things. Yeah. And we're going to do like, one of these or something ourselves, but we hope other people come to us with better ideas. Yeah. So non-goals of the project. First thing, we don't want to reinvent mesh networking ourselves. That was right off the bat. We said we're going to use best of breed, somebody else's solution to mesh networking. We thought that was going to be easier than it turned out to be. We just assumed, given the number of publications in this area, that the maturity of the software somehow was related to that. And it turns out that a lot of the solutions that are out there, so far they haven't been effective for us, and we're kind of hobbling along. What's that?
Because you're using FreeBSD.
Yeah, that's why I'm here today, so we can talk about our options in that area. Okay. So we also want to support other research groups that want to do mesh routing. And if I have a graduate student who wants to do mesh routing, good. I'm not going to go into this space, but that wasn't our goal going in. The other thing that we're really adamant about is no public Wi-Fi. A lot of people look at this network and they say, well, why don't you use it to provide public Wi-Fi. There's two reasons. First reason is technical and the other is political. The technical reason is if we have to provide public Wi-Fi, we have to ensure that the latency and the throughput is good enough for people browsing the web, and that constrains us to the point where we can't do other things that might be interesting. What's that? Potentially on the hook for security. And then the other is political, which is Cambridge and Boston already have these public internet projects, and we don't want to be seen as competing with them. Yeah. So if someone else wants to come and try to do public Wi-Fi on our network, then they're welcome to do it, but that's not our goal. Yeah. But we don't think that our network's going to be good for public Wi-Fi. We're not designing for that. Okay, so here's an actual picture of the current deployment. And the BBN campus is up here, and we have about 5 nodes there. And the Harvard campus is down here. And I guess it transitions from winter to spring some here. I'm not sure what's going on. I knew that Boston weather was highly variable, but I didn't realize it was like that. There's something going on. Yeah. And the distance between these is roughly 3 kilometers. Yeah. So right now we don't have direct wireless connectivity between these. We could probably do something with good directional antenna, but it's not going to be line of sight anyway because of buildings and things like that. So that's not really our goal. So our question is, how much of the city do we end up spanning? And it turns out this is much denser than that cartoon that I showed you at the beginning of the talk. And we're not getting great network performance even with this amount of density. So the question, I think this is part of the answer, the thing that we need to answer is, how much density are we going to need to get decent network performance? Are we going to be able to fill in this whole space or not? Yeah. And this is, by the way, about 1/3 of the picture of Cambridge that I showed you before. It's not the whole thing. So the Harvard, yes? RoofNet's not available. It's not functional at this time. So we have like a couple of nodes on there. This is the CS building, a couple of nodes here. There's a couple of nodes. You know, this is just for sense of scale. That's about 50 meters right here. This is about a couple hundred meters. Yeah. The BBN deployment. Those are on rooftops at Harvard. One of the cool things is, you know, because we own the buildings, we can go to the people and say we want to put this on the roof, and they'll let us do it. With the city streetlights, we got to get the city involved, and so the BBN folks are pushing in that direction. Okay, so sensors. We've been playing with a bunch of different sensors. The first one we started with is this Vaisala weather sensor. Has anybody seen this sensor in this room? This is a fantastic sensor. So it's this nice thing. It's about the size of a large coffee thermos. And it's got wind speed, direction, precip, pressure, temperature, humidity. It is extremely well calibrated. It has an RS-232 interface and some ugly ASCII protocol that it uses, so you have to write the code for that. It's got a heater inside that melts off any ice that forms on it. It was designed by a company from Finland. You assume they know how to do these things. And there's no moving parts. So the way it does wind speed and direction is by listening to the angle of arrival at these 3 microphones here. Yeah? And it determines rainfall by counting the raindrops that hit this dome. It's awesome. And it also costs $2,500. So this is like 5 times the cost of the node hardware. So you're not going to have 100 of these. The good thing is that we budgeted 100 of these. But you don't need 100 weather sensors even in Cambridge. Yeah, so that gives us some padding on the budget for other things. Very, very accurate, very, very well designed. We've looked at sensors for air quality monitoring. The public health folks that we work with concentrate on something called PM10, which is particles below 10 microns in size. And that has to do with the exposure and how it gets into your lungs and things like that. The sensors for tracking those things are you know, they do studies now where they walk around with a backpack with a sensor in the backpack and a GPS receiver so they can get the concentrations at different points. Unfortunately, these sensors are really not designed to be deployed outside permanently. They're designed for, you know, laboratory use and occasional use outside. But they require an annual maintenance cycle. It's a few $100s. You have to send it back to the manufacturer to get it cleaned out. And so even though it's reasonably priced and it does what they want, it's not clear for other reasons that it's the right sensor. So this is an interesting question right off the bat, which is, how do you get the right sensor for an outdoor permanent deployment? Yeah, that's got the right fidelity. Noise pollution. Well, we said right at the beginning of this project, and when we got written up in the Boston Globe, all the reporters asked me this, so are you going to put microphones and cameras on the nodes? And I think there's a lot of exciting applications that would involve cameras and microphones on all the nodes. At the same time, you know, I'm a professor at Harvard. This is the last thing you're going to tell the newspaper that you're doing. So we decided no cameras, no microphones. I think it's just it's just something you're just not going to do as a university. But that doesn't mean we can't do noise pollution. This is a noise pollution sensor. It basically gives decibel levels integrated over 10-second periods. And that's actually all you need for the kind of studies that the public health people want. You don't need waveforms. Now, you would need waveforms if I wanted to distinguish trucks from, cars or something like that, yeah? But, so it's a trade-off.
But you already have waveforms, right? You have the time differences of arrival on your wind speed.
No, but it doesn't give you that information at all. It doesn't give you that low information. It just tells you what the wind speed and the wind direction is.
But the information is there. That's what you're saying. So
If I could tap it in, and likewise, the information's here somehow if I could tap into it. Yes?
So what's the extensibility story for sensor attachment to your node?
Great question. Right now, we basically have a standardized mil-spec connector with a certain number of pins. And if you need to attach a sensor to our node, you build a connector that has the correct mating on there. So it's basically RS2. We're bringing out RS-232 in USB, but not through a standard connector. We have our own connector, which also has 12-volt power.
Additional connector for each sensor, is that?
Right now, this is something the BBN folks are doing the hardware side, and so far, based on the case design they've chosen, and this was, we're not allowed to put anything on the streetlights we want. The city was very adamant that they have a say in terms of what the node looked like, which I was surprised that they cared. They said, okay, this is the type of case we're going to let you use, and this case only has one port that comes out for a single sensor. So for now, the story is one sensor of some type per node, but I'm pretty sure that could be changed in the future. Yep.
Some of those sensors require powering. The other ones don't require powering. You can just read out the line.
So with USB, that might be okay if they don't
USB
require too much
because
power.
there's two power lines.
Actually, when I asked about extensibility, I didn't think about the ports at first. What I thought about is somebody's going to have to clamber up there and put another sensor on it.
Huh.
No, you cannot, right?
Yeah,
Well,
sure.
once it's okay. So this is what we would like to do.
Ports you have,
What we would like to do is imagine that we're going to deploy a network. It's going to have some sensors in some physical locations. If another research group came to us and said, "Here, we got a grant from the NSF to go do something, and we want to tie our new sensors into your backbone," they can pay for new nodes. They can pay the city. They can pay us basically to go to the city and install them and all that kind of stuff for them. And we will weave their nodes into our testbed as long as those nodes are open, just like all the other nodes are. So that's the stipulation, is that we're not going to carve it up into little bits and pieces. Yeah, so it becomes a community resource. We haven't formalized that yet, mainly because we haven't gotten to that point. But that's the thinking right now.
You can talk about the programming APIs.
Come in there. Yeah, okay, so, and lots of other sensors. So let me keep going and just try to get into the fun stuff. Okay, so the networking, we started with 802.11 mesh as the backhaul network because we assumed that that was the most cost-effective thing to do. Now keep in mind, the data rates we're talking about tend to be fairly low. The sensor data rates are not incredibly high, a few hertz at most. But there are high bandwidth things that you need to do occasionally, like reflash the node with a new OS image. Yeah, but that's not necessarily something that needs to get done every day. It's not something that needs to be done quickly. So we made some back-of-the-envelope calculations and said, look, assuming what we know about wireless mesh, multi-hop, and so forth, we think that 802.11 mesh is going to be adequate for this. And it's cost-effective because all you got to do is buy the radio and the antenna and, of course, invest 4 graduate students for 6 months to get the network to work, and then you're done. Yeah. In retrospect, and this is not off the table, we might imagine going away from mesh and using like a GPRS modem or something like that instead, although that would probably involve some subscription fees or something like that. Mainly we decided for mesh because when we wrote the proposal, we thought that was just going to be the easiest thing, and we were going to go and grab the RoofNet software and use it, and we were going to be done. So far that has not happened. It's actually been quite a lot of effort to get the mesh to work. The radios that we're using right now, we're using a 900 megahertz 802.11 radio. This is non-standard, and it's very, very high power. And the vendor claims something like multiple kilometers of range with this kind of radio. Of course, that's line of sight and things like that. The experimental radio, we're using the Wistron CM9. Both of these are Atheros-based, and the reason for that is because, well, there's pretty good open source drivers and things like that, so people can get down there and hack them. If you guys have suggestions for other or better radios, I'd love to hear it. It has taken us quite a long time to settle on this configuration. Weird things start to happen. You put 2 radios on this motherboard, you run them both simultaneously on max power, it reboots the node because the motherboard can't provide enough power to both of the PCI slots at the same time, this kind of thing. Yeah, the drivers, at least under Linux, were falling over all the time in the dual radio scenario. So this is not the only configuration we tested. We tested many more radios, many more configurations, and this one so far has seemed to be pretty stable. Yeah. We're also budget limited in terms of a number of hundreds of dollars per radio that you can afford to buy.
Are the drivers are previously open source?
Yes. I don't know about the HAL issues though.
And the driver works on 900 megahertz and
Yes, it just works. So basically, this 900 megahertz radio acts like it's an 802.11b, and when you tell it to go on channel 6, it actually goes onto some other funky internal channel that's the 900 megahertz band. So it fakes it out. Actually, I think what's going on is the radio is a 2.4 gigahertz radio internally, but it has a mixer down to 900, which means it actually interferes somewhat with the 2.4 gigahertz radio on the same motherboard because there's a little bit of leakage. So things that you just, I try to be a computer scientist, not an EE, but you have to deal with this stuff. Yeah. Okay, so with the mesh routing, I mean, we were surprised to find that the off-the-shelf things that you could just go download and try to use didn't necessarily work as advertised. And a lot of that is because our configuration is so different. There's a lot of anecdotal evidence out there about what works and what doesn't. There's very little in the way of good published empirical results. So people say things like, oh yeah, well, we use this driver and that routing protocol and this radio and, and it seemed to work. And they were happy with that situation, but that's not necessarily something that you can reproduce yourself. Yeah. So right now we're using OLSR NG, which is an enhancement of this very commonly used OLSR protocol. It has a lot of problems. The main advantage of it is that there are 2 pretty big deployments in Berlin and Vienna using this routing protocol. Basically, it's a community wireless LAN project, and people have put these nodes on their rooftops and gotten themselves free Wi-Fi by linking into this mesh network. And so there's hundreds of nodes. The problem is there's basically no published results on the performance. So it's all anecdotal in terms of how well it's working. Turns out the protocol has routing loops and all kinds of other problems all the time, which is, because it's people getting free Wi-Fi, they don't mind so much. They just go and reboot the node if something doesn't seem to be working, and it usually fixes itself. So there's a very different human-in-the-loop scenario than what we're anticipating with this network that has to basically run all the time. There's a follow-on project from the same group of people called Batman, and it actually stands for something, and I don't know what it stands for. And they claim that Batman is designed to be much more scalable and much more efficient. And part of what's going on with OLSR NG is the protocol was extremely CPU intensive, and it was spending a lot of cycles on every message that it was routing and all the control traffic. So the load averages were up in the 90s just running the protocol. And now they've brought it down to like the 10-15% range. So there's a lot of engineering issues involved beyond the kind of algorithmic aspects of the protocol design. So here's one picture. We have a lot of other data, but this one's just kind of instructive. So this is about 3 days of data, and this is the throughput in megabits per second over 5-minute averages of 2 nodes that are on the same building, rooftop, same height, 8.5 dBi antennas, 50 meters apart. Okay, so the best possible case. Yes, no obstructions. Yeah, perfect line of sight, all the great stuff that you want. And look at this variation in the throughput. Now, you might say this is diurnal. It's not diurnal. The spikes do not happen at the same time every day. It's unclear right now what's going on. This is temperature data from one of the sensors, and so it was unclear whether there's any correlation between temperature. Maybe it's based on humidity. I don't know. Have you guys seen this kind of thing? In this case, no, but and this is in the middle of January, so in Boston that would be snow, but it wasn't actually snowing either during these days. Surprising. Okay, so we don't know what's causing this variation, and it may just be something that we've done wrong, but we spent a lot of time trying to fix these things. At this point, the way I think about this is work around this, work on top of this, don't try to fix it. We might be able to fix it, that would be great, but assume that the links are highly variable, they may come and go, and of course you've got to worry about things like nodes crashing and all of that. So the core research question that I'm interested in as a CS person is, assuming that I have this network of a large number of devices, and this is not the same as a data center, they're basically linked together with these slow, highly variable, not very robust links. So more DTN style, yeah? How do I design distributed services to run on top of this, yeah? So an example, so the picture being, okay, here's my network, here's my crappy mesh, the dotted lines are supposed to be related to how crappy the links are. And then I want to run things on top of this to allow me to control the network, monitor its health, upgrade the software on the nodes, deploy applications, start and stop various services. Yeah, all the things that you need to do to run an open testbed. Yeah? Now, if I had a wired back channel to all the nodes, we'd be done. We know how to do this. And there's all kinds of software we could use, like Planet Lab and EmuLab and all those kinds of things. But now we're kind of faced with this very poorly provisioned network. How do we do that? And it requires that I think you rethink a lot of the assumptions that are made for doing that kind of distributed systems management. Yeah, the protocols that you use. How do you think about shared state? How do you think about consistency? Right? Yes?
How different is this than some of the problems faced by satellite networks?
So I was just about to say the closest thing that I can think of here is satellites. Yeah? Where you don't always have connectivity to them, and I don't know about their failure rates and things like that. So I'd love to understand, but my guess is that satellite networks are not designed to be programmable by anybody sitting at a web browser and pushing code in there. Yes? That you take a lot more care in terms of what the applications are doing, and you test the hell out of it before you deploy. We're not going to have that luxury here. We're not going to be able to tell people that, look, you're not allowed to run your thing on CitySense unless it's gone through, this set of regression tests, and we know exactly what it's going to do in advance and all that kind of stuff. We're not NASA. Yeah? If we want this thing to be useful to people, we're going to have to accept a certain amount of failure, yeah, and poorly written code and all that kind of stuff. So that's where I want to go. And basically our guiding principles here, and this is where we're now at the point of articulating the architectural requirements. Asynchronous messaging. Don't assume you're just opening up TCP end-to-end TCP connections out to all the nodes. That's a big mistake. Weak consistency, of course, because if we require strong consistency on most things, then we're just not going to, it's a non-starter. You're never going to get it. And frequent recovery. So G2 asked, how are you keep this thing up and running? Well, one of the techniques, and I think this may be on a future slide, we're putting a grenade timer in each node, which is basically one of those vacation timers you get for your lamps when you go out of town. It will reboot the node at like 3 in the morning every day, irregardless of whether it's happy or not. And the point there is, if we can get it rebooted to a known good state every 24 hours or so, I think we're going to be suffering much less problems with things like memory leaks and weird state accumulation in the routing protocol and other things biting us all the time. So I'd much rather have a network that reboots every day than one that I have to worry about uptimes in excess of 30 days or something like that. Well, that's actually a really serious problem. If they reboot at the same time, we're going to be in big trouble. Yeah, so we need to stagger it, and we don't really have a good methodology for that quite yet. We need to think about how to do that.
And if you're updating the boot procedure with the new OS at the time you just happen to.
The beautiful thing is, if we schedule things correctly, we'll know when the reboot cycles are happening, and so we can avoid them. They're not going to happen at random times. They're scheduled. Yeah? Okay, so programming model. We've had a lot of arguments and heated discussions in the research group about the right way to think about programming this network. And it is obvious that no one programming model that we come up with is going to make everybody happy. For everything that I propose, Rohan jumps down my throat and says, oh, but what if you wanted to do this or this or this or this or this? And I have to say, well, I'm sorry, you can't do all those things necessarily. So there's always trade-offs involved. The first most obvious thing, and this is what we have right now basically, is we let you log into the nodes via SSH and you can do whatever you want. This is probably less than ideal. Yeah, for somewhat obvious reasons, but it also means that users have to do a lot more work in order to make sure that it's doing what they think it's supposed to be doing. The other thing is that providing like Unix shell access is, I think, fundamentally a misleading interface to provide, because if people start treating it like they treat Planet Lab, they're going to be hurting in terms of making it actually work for their application. They need to realize that things are asynchronous. Things are going to fail. The networks, you can't just SCP 10 megabyte log file and expect that to work. Yeah, so if we set the expectation incorrectly, I think people will use the network in the wrong way, and then they will be disappointed and they'll go and do something else with their lives. Yeah, so it's better to provide them an interface that matches the capabilities of the testbed better. The other option is to do you take over the node completely by providing us with your own customized OS and kernel and routing protocol and everything, and we basically reflash the node with your image and reboot it into that image before you run an experiment. That gives you ultimate control over what the node is doing, but it doesn't allow any degree of sharing. This is basically what Emulab does and Orbit does. Yeah? So it's the highest fidelity thing to do, but it's not shareable. And of course, it is incredibly high overhead for pushing those OS images out. Yeah? And so it's very slow to iterate. And if you break, well, yeah, so the way we actually have it set up is there's always a golden image on the node that we always boot into the golden image, and we design the golden image, and once we've decided what the golden image is, no one's allowed to touch it. And option 3, and this is where we're going right now, is basically more of a managed application environment model, and this is the kind of obvious thing, but basically sort of like Planet Lab Application Manager, if you're familiar with that. The idea is that we provide a web front end, you upload a tarball of what you want to run on the testbed, and that tarball contains a script that has several commands: deploy, start, stop, decommission. Yes? And we handle the action of pushing that tarball out to the nodes through some mechanism. We didn't tell you whether it was SCP or BitTorrent or some sort of efficient dissemination protocol or whatever that we came up with. That's abstracted away. So you don't get to have control over that level of the network. But the idea there is you get to deploy your job, and then we can decide when it gets to run based on things like, well, if you said you wanted to run on all 100 nodes of the network, do you actually want it to start as it gets deployed on each individual node, or do you want them to all start at the same time? Yeah? So it means taking control away from the user, but it gives us a lot more control over what the network is doing. One of the biggest concerns that I have is resource management. And Planet Lab, by and large, got away without addressing this problem until fairly recently. And it's not even clear that they've completely addressed it yet, because they started with fairly well-provisioned PCs with lots of memory and pretty fast CPUs and fast network interfaces and lots of disk. We don't have all of those things. Our nodes are pretty resource limited. They're not moats, but they're not, servers either. So doing the kind of best effort time sharing thing, it's clear already from our experiments and our competition for this test bed so far that it's not going to work. That if I'm running an experiment and G2's running an experiment, we're both unhappy, and it just comes down to who wants to yell louder at the other person. And this is not really the right way to doing things. So batch scheduling seems like what a lot of people would like. They want to own the test bed for the duration of their experiment, but that's going to preclude things like long-running experiments that, for example, is just collecting sensor data in the background and pushing it to a database. That doesn't really eat up a lot of cycles. So our current approach is a hybrid system that lets you have multiple lightweight background experiments, and those are going to be fairly resource constrained, like in running as a cron job, basically, and one single intensive experiment riding on top of that. What it means is that that intensive experiment that you're running has to coexist with these background jobs. So you never get to completely own the node 100%, but you maybe get 80% of the node. Yeah, I don't have anything on here on this. I have 2 students right now working on this problem. This is a big, big, big challenge. Sharing the network is a big challenge. Oh, maybe I do have some. Do I have some slides on this? I'm not sure if I have any slides on this. Essentially, the backhaul network, the 900 megahertz radios, we're not making any guarantees about their performance. So effectively, we're just going to let people do whatever they want over those radios with the understanding that they may not see good throughput. The experimental radio seems to be a very precious resource, and something that people are going to want to do things like change the physical layer bit rate and change the channel. So our current thinking is the single intensive experiment is going to be able to control that radio and get exclusive access to it, and the background jobs only use the 900 megahertz radio. Yeah. So if you're experimenting with a mesh routing protocol, you don't, you do get exclusive access to that radio. Yes.
How about sharing, say, across the network? Say you give some nodes to some intensive experiment and some other nodes.
So effectively space sharing. Yeah, we can definitely do that. That would be very easy. So far, I haven't even talked about that because we have so few nodes, but certainly we could carve it up. Yep.
Sensors are all read-only, right? So they can easily be shared.
That's actually not 100% true. So like this Vaisala weather sensor has commands that let you set the rate and the precision and the data types and all the things that it produces. So the question will be, do we need people to get control over the sensor or not? Right now, we are taking control of the sensors. We are building little daemons that talk to the sensors at some rate that we think is acceptable for most people, and we just publish that data. You just look at /dev/sensor and you get the data. Yeah.
I can see places where this will be useful when multiple queries comes in and they want to optimize over a set of queries but with different sampling rate.
That's right.
And you want to optimize across.
That's right. So we are operating at a much lower level than that right now. We're basically saying that's like an application I would love somebody to come in and build, is talk about how to do that optimization. But we're basically providing much lower level access to things because we don't know what people want to do there yet. There's a tension here between providing too much structure and not enough. All right, I'm going to skip over the experiment control. I mentioned this already. We're not going to have remote access to the nodes once they're deployed, so you can forget about going and rebooting things if it stops working. Yeah, it requires calling up the city of Cambridge, getting one of their electricians to come out with a cherry picker. They don't like doing this in inclement weather. It costs money for us, and every time we do it, we lose some brownie points with the city, and we don't know how many brownie points we have. So essentially, we never want to have to physically touch a node once we've deployed it. This is keeping me up at night because we don't know the best way of solving this. As I said, right now my approach is the grenade timer. That means that the node reboots once a day. We also have a hardware watchdog that's on the motherboard. That's already there. But the question is, how do you tickle it? So the watchdog can reboot a node if it's not happy. You have to decide at some higher level in software when it's not happy. Right now we have a script that basically once every minute asks some things of the node. What's your load average? How much free memory do you have? How much free disk do you have? Can you ping other nodes in the network? Do you have any neighbors in the routing table? And can you connect back to the main server? If all those things are true, then we stay up. Otherwise, we go down. The question is going to be, as you build out this network and make it very large, how sensitive is that decision to reboot? Because if it turns out that, somebody's deploying an experiment and that's choking up the wireless network, and so some large number of nodes can't ping the home server during that update procedure, and then they all decide to reboot themselves, yeah, you have a problem on your hands. So we don't have experience with that to say what's the right solution.
And what if you have a power outage? Then you're going to have everyone rebooting at the same time.
There's a power outage. Oh, you mean at the home node? Yes.
Cambridge's power outages every year.
Yeah, so if our home server goes down and everybody calls home and they can't get to the home server, then they're going to reboot themselves. Yes, that's a problem. So the logic needs to take into account, like, well, if I haven't been able to talk to the home server in longer than some period of time, maybe I should do some exponential backoff in terms of my future checks so that I'm not just constantly rebooting. So it needs to be stateful across reboots, which adds a whole bunch of problems.
Well, I think he was also wondering about the case where the entire city's powered.
Then the nodes are down because they're powered from the streetlight. So if the
Right, but it goes off.
oh you mean if the power goes out and then it comes back on, they all boot up at the same time.
Yeah, which happens.
We can't control that.
But yeah, it's going to happen.
It's going to happen, yes. Hopefully it happens rarely enough on a large enough scale that it's not going to kill us. It doesn't happen that often. Really?
You're living in a different part of Cambridge than I lived.
It's true. Yeah.
For the golden image, is your plan to never change it?
My plan is to change it under intense scrutiny by a panel of experts who will vet any change to that piece of code once it's been deployed. Yeah. So code reviews and all that fun stuff. But rarely. And so the question is, what does the golden image do? What does the golden image do? Right now, our golden image puts the node into kind of an administrative node where it does attempt to join the OLSR network, so if things happen to be happy, we can get into it. But it also acts as an access point, so on the experimental radio. So you can drive up to the node and with your laptop talk to the thing up on the street light and hopefully SSH into it and fix whatever's wrong with it. Yes?
Is there some way I can test my software in the lab before I send it out to the streetlights?
Thank you. Yes, that's a great idea. In fact, we have a 20-node indoor test bed where all the nodes are wired to the Ethernet as a crutch. So this is the Play School version. Yes, and that was one of the first things we built because we knew that that was going to happen all the time. Yeah.
Crutches, you guys can't put with the power socket? Any kind of, even like a 14.4 kbps power line network to get to this?
Really? You're interested in power line? So I think, again, when we came up with the budget and all the equipment that we decided to buy, we made some early decisions. We may change the node design. This is version 2. We may have a version 3. I don't know yet whether that would be an effective thing. It might well be the right model. Yeah, but it might well be the right thing. As I said, or GPRS or some other kind of backhaul technology. If there's WiMAX in Cambridge, we could use WiMAX, potentially. How much time do I have? I'm sorry, I don't know.
We take another 15 minutes.
Okay. Yeah, I'm almost done anyway. So the software updates, this is one of the biggest challenges here because anytime we want to patch something on the node, we need some ability to push out potentially new OS kernels, new libraries, configuration files, all those things. So we've already spent quite a lot of time optimizing that. The obvious thing to do, just SCPing stuff over to the node, just does not work, especially when you have a lot of nodes and it's multi-hop mesh. So we've thought a lot about, well, could you do like a BitTorrent style dissemination protocol? And I think there's definitely some interesting research to do in that. Right now, we kind of have a cute hack, which is we use rsync on a hop-by-hop basis, but we do the rsyncs over a spanning tree. So that means I update my immediate neighbors over rsync, and they update their neighbors, and they know who their neighbors are by looking at the OLSR routing table. And that means you're never doing anything over longer than one hop. And rsync is an efficient diff-based updating protocol, and so it only exchanges the amount of information that it needs to in order to update things. So if I make a one-line change to Etsy password, I don't have to update a 64-megabyte image. I just basically am pushing a small amount of data. This seems to work really well, and the cool thing is, it's just a shell script. It didn't require going and writing some fancy new complicated protocol. It's pretty simple. Yes?
Back to previous discussion. Did you consider having an infrared option as the way to reboot them?
What we have actually, you're thinking of kind of a local power switch. Yeah, so what we have, I have an undergrad working on this for a senior thesis right now. He's building a USB dongle that attaches to the node's USB ports, powered by the USB port. It has its own processor in there, and it's actually hooked up to the power supply, so it has physical. The problem with the motherboard, the watchdog on the motherboard, is it only resets the motherboard. It doesn't reset like the external sensors and stuff like that. So we want to literally get our hands on the power supply at that low level. And it's going to be basically a moat radio. So he'll have some simple protocol. So if I walk by with a moat and you know how to send the magic packet, you can reboot the node that way.
Which undergrad's that?
Oh, his name's Amal. He's a senior this year. Kahiri or something is his last name. Yeah. I think he's a EE. Hey, Microsoft Technologies come into this project too. Great. I was going to do a live demo, but unfortunately I couldn't get on the internet, so I took screenshots at the hotel. So we do have a SensorMap award. Thank you very much. We are using SensorMap to do the visualization. We cannot wait for version 2 of SensorMap because there's all kinds of things we'd like to do that don't seem to be easy to do with this version. Basically, this is the BBN network here. Does everybody here know SensorMap? I'm assuming everybody is familiar with it. It's basically an interface to real-time sensor data through virtual Earth. And the sensors appear in SensorMap, and the icon, I guess, represents that it's an unknown sensor type. That's what the question mark means, yes? And when you hover your mouse over the sensor, it pops up a window that goes and fetches something over a URL on the web that, in our case, is a continuously updated graph of the real-time sensor data that we've collected from that node. And just because I don't know if we can fix the size of that box or not, but it gives it a small window, so you have to scroll around. But if you click on that, you get web page that shows you all the data from that node, and I can just go and visualize it. Right now, we're not using the full feature of SensorMap in terms of turning this into a temperature sensor, which would be a nice thing to do, but mainly because there's so many different sensor modalities here, we didn't know the best way of doing that, so we left it as an unknown or generic sensor type.
The other one you might be able to use is to actually use that to visualize your link quality.
I know.
Very
so
similar to a temperature control map, except that this is the link quality data.
So what I really want is to, and I'm actually working on this right now, is I'm collecting lots and lots of network measurements, and I've been struggling with the right way to visualize this. What I'd really like is to overlay edges on the graph and color them according to the quality of the links, and be able to navigate that and click on a link and see a history of its throughput to a neighboring node. I don't know if that's possible.
I mean, that's a heat map that Lishan probably can show you afterwards. Right?
Yeah.
I did it with the Swiss experiment.
I saw the heat map, but this is slightly different because it's more of a graph with edges rather than painting every pixel in the space with some value. I guess I could turn it into that. Yeah, all right. So it might be possible to do that. That'd be cool. So we actually have all of our nodes, and I was going to do the live. Is this my only slide on this? Yeah. I have all of the nodes. We have 20 nodes inside at Harvard, and we have 5 at BBN and 5 at Harvard. So about 30 nodes in total in SensorMap right now. And if you go and navigate, and you have to type Cambridge MA, and you should see both the Harvard and the BBN nodes floating there, and you zoom in, you should be able to get the data. So if you're on the internet, I hope it works. I don't know, you might want to tell me. Or don't try it. Don't try it, because it doesn't work. But it's been actually really nice to have all that in real time, so that basically it's on the front of our web page too, so anybody who wants to go in and just click on a node and see the sensor data can do it. They don't have to learn SQL. The health of the nodes themselves we're monitoring using a tool called Ganglia. This was developed at Berkeley for monitoring workstation clusters, but the cool thing about Ganglia is that it uses UDP packets to send the data, and that's great because it means that you don't have to maintain TCP connections. And it basically sends periodic updates on the health of the node back to a central server. So we're just using Ganglia to monitor the health of the nodes, and that's awesome. So what it gives you is a web page that looks like this, and this is somewhat out of date picture here, but you can see each of the individual nodes here, and this is their CPU load. And it turns out you can look at CPU load, network throughput, memory availability, disks usage, and it can color these graphs according to how loaded they are and all this. So it's really designed to get a quick snapshot view of the health of a cluster, and then click on a node and get detailed view of that. So it's cool that we didn't have to build that tool from scratch. It's actually working just fine on these nodes. Okay, so this is kind of wrapping up. The mesh routing, I think, it's not a closed book, and we would love to work with people that want to help us get the right mesh routing solution for this network. A lot of the work that's happening right now is largely community driven, by which I mean people who are hacking things to get them to work in their grassroots public Wi-Fi experiments, not scientists trying to get something that they can publish papers about. And as a result, it's very hard to understand what works and what doesn't for real. Yeah. And so RoofNet was an example of a project that was done through a university group, but they're all off doing their startup now. So we can't really leverage their expertise unless we buy their products. The link variability is much higher than expected, and I'd love to hear your thoughts on why you think that's the case. But we were shocked to find that even just 2 nodes right next to each other were having such high link variability. We have to think about this as an untethered architecture and not a tethered testbed. So we can't just pick up, we've had conversations with Jay LaPro and Mark Fujinsky and all those guys about why don't you just install Planet Lab? Why don't you just install ImuLab? And it turns out you have to make some very different assumptions when the nodes don't have a wired back channel. It changes fundamentally the way you think about it. And so I didn't want to go and reinvent Planet Lab for this project, and I still hope we don't have to do that entirely, but there are going to be some things that we have to change to make it work. And this is being recorded on video, so I shouldn't probably get into too many details about the political issues that we've run into, but just let's say that it's actually been incredibly enlightening working with city government to understand what their concerns are. I made the naive assumption that they would just embrace this project with open arms, and in fact they wrote very positive letters of support for our NSF proposal. That doesn't translate necessarily into willingness to work so easily with us when the funding actually comes through. And so we've had to put in quite a lot of effort into educating them about what we want to do, what the implications are for the city, what kind of costs it might incur for them. We actually have budget to pay them for any kind of expenditures that they might have for this project, but there's an opportunity cost because they own the streetlights. And if they give Harvard access to the streetlights, that might have been something that they could have exploited for some other kind of financial gain in other ways that they hadn't anticipated. So there's a lot of discussions about whether this is the right thing. Fortunately, Cambridge MA is not the only city in the United States or anywhere else in the world for that matter that might want to do this, and we have been talking with some other cities and also working with Harvard and BBN. To the extent that we can do things on our own campuses, we're going to do that because we have a lot more control over those environments. Okay. Yes?
Something related. There's another school down the road, not too far from where you are. There's a project called Cartel. And that's
Is that vocational school?
Well, the bridge next to it is called Harvard Bridge. I don't know why.
That's right. I don't know why. I think because we used to own it.
So if you think about Cartel and this bunch of moving nodes and directory and networking, do you think actually it could be coupled with your street pole to actually have something that's more than either CitySense and the Cartel can do?
Yes, absolutely, 100%. That's something that I very much want to do. So I talk a lot with Sam about, at some point we need to get together. Once our network is deployed, I think they very much would like to look into doing that. So Cartel, they've got sensors mounted on taxi cabs and things driving around the city, and they're collecting data that the taxi cabs can gather. We can gather data at all points in time for certain locations in space. They can collect data from many locations in space, but more temporally distributed. So the question will be, can you synthesize and merge those data sets into something that's meaningful? We've thought about, and I've got a graduate student working right now on that problem of what's the right way to do interpolation on that kind of data set. So if I wanted to pretend that I knew what the data was at this point in space and time, but I only had an ephemeral reading from a taxi cab that passed by 6 hours ago, plus a couple of readings from more distant CitySense nodes, what's the right way of thinking about estimating what that value would be? And it turns out it's such a hard problem because it depends so much on what the sensor field is like. If you're talking about air particulate counts, it depends on very microscopic turbulence patterns in the air. And it turns out that doing the modeling of how air particulates travel through the air, it doesn't fall off linearly in some simplistic way. Noise pollution seemed like a really nice one because you would imagine, well, noise, that sounds obvious, right? How does sound propagate? We have a good understanding of that. Well, it's actually not so simple. There's a nice project that they did in London where they came up with a noise map of London. You can go on the website and download this fantastic map of the city of London with their estimates of what the noise pollution would be at every point in the whole city. It's a model. It's not based on empirical data, but it's based on empirical data and it depends on many factors. The road traffic, the surface condition of the road. Is it a cobblestone? Is it paved? Is it, right? The configuration and the heights of the buildings, the construction materials. Basically, there's like 80 variables in this model that they have to crunch in order to figure out what the noise pollution would be at different points. As far as I can tell, they don't actually have the empirical data to validate that. One of the things CitySense might be able to do is help feed in some more of those measurements. But it's clear that the modeling that you have to do to do that interpolation is pretty sophisticated. It's not simplistic. But yes, I'd love to combine this with mobile sensors and things like that. Okay, so we have a bunch of collaborators in the public health area, air pollution, looking at disease epidemics, people who want to look at water quality, and there are some people who've talked about video sensors. We have to figure out whether we can support them or not. And basically that's it. So we're very happy to be in the position to work on this project. It is turning out to be a lot harder than we thought going in. We have a lot of good experience so far with our deployment, our small-scale deployment right now. We're in the process of going and getting all the data and cranking the numbers and writing papers and that kind of fun stuff. But what we're hoping to do is, by the end of the summer, I would like to open this up so that people can start programming it and using it. I think we're now at the point where the basic system software is stable enough that we can do that. Thanks. Any other questions?
So how big do you think the network is likely to be at the time when you plan to open it?
The end of the summer, I mean, it depends on how you count. I would like it to be 25 to 40 outdoor nodes by the end of the summer. This is going to depend. At this point, we have the ability to crank out the nodes because we've settled on the case design, the radios, the software, and so that's a lot easier than it was a year ago. But it's going to depend on what issues we have with identifying the locations to deploy them. That seems to be the bottleneck right now. So if we're lucky and City of Cambridge is happy, I mean, basically we got real lucky. Last week they just said, oh, you want the cherry picker? You want to go put some more nodes out on streetlights? Let's go for it. And they just put up 5 more nodes for us. That was surprising. So if it continues in that vein, then it should be easy. But if we run into more issues with the deployment itself, then it's going to be harder. The density, my biggest concern actually is the density. We do not know yet what kind of density we're going to need to make this thing useful. If it turns out that the nodes have to be extremely tightly clustered, then it's less clear how useful that is to people.
Yeah. With the graph that you showed before, was that using the 900 megahertz radio or the 2.4?
Yep. Oh, you mean that graph of the bandwidth variability? You know, I don't remember now. That may have been 2.4 because at the time those measurements were taken, we still were debugging some issues with the 900 radio. Oops.
Aren't there like mobile phones operating
This
on
here.
those frequencies?
900?
Like not like cordless phones.
Yes, of course there are. There are also cordless phones in the 2.4 range.
Yeah.
So it's unclear whether we're causing interference from other people.
Or vice versa.
Yeah, but it's unlicensed ISM, so there's nothing illegal here.
No,
It's just
I'm
unfortunate.
just saying that one of the explanations.
We'll interject some sensor data in the middle of your conversation with your
Do you
mom.
have a spectrum analyzer so you could see if interference is causing these fluctuations?
Yeah, we do. We just need to sit down and do all that. Yeah. We played around with it. We could not. This was just, we had no idea. Because part of it was, you go out there, I mean, it's the middle of, now that it's warming up, maybe it's going to be easier to do. But you go out in the middle of January and you don't want to spend more than about 10 minutes out there. And these are, remember, these are over 5-minute averages. So you'd really, have to be on your toes and say, oh, wait, hold on, we're seeing this kind of thing. Let me go out there and look at the interference. Now I am running lots and lots and lots. So this was very painful data to get. We didn't have the infrastructure to go and do these measurements and log everything and to get it all into a format that was usable. As of last week, I have programs running that are doing all-to-all network measurements, including TCP, UDP, and ping measurements to between every node and every other node. Because we have so many nodes, it's taking 2 hours to run those measurements. And so you only get roughly 1 data point per link per 2-hour period. Unless I start doing things like running multiple links simultaneously, in which case I'm causing interference, I'm trying to be careful. And so what I need to do next is go and visualize that data and look at that variation over time and see what happens. We know from our experience with MoteLab, which is our sensor network test bed, we have about 200 nodes inside. We've been running that for 3 or 4 years. That MoteLab sees a tremendous amount of diurnal variation. So the bandwidth between the nodes goes up at night, goes down during the day. Is it because of doors being open and closed? Is it because of people using their laptops? Or is it because you have many more absorbers of 2.4 gigahertz energy in the building during the day? I don't know. Okay, well, thank you very much for having me. I know you guys have been really busy interviewing, and I'm not interviewing, but I really appreciate your coming. Thanks.
Thanks, Matt.
Thanks.